Hey, this is Mr. Ayton. This is the 2022 AP Chemistry Free Response Exam. This is going to be question number 1. If you're a teacher or you're a student and you want to prepare for AP Chemistry or you just want more, go to MrAyton.com. This is my website. I have hundreds and hundreds of multiple choice questions, free response questions, daily free response questions, all at a reasonable low price. But let's get to the AP Chemistry Free Response question number 1. This is the May 2nd exam in 2022, and this exam starts off with a stoichiometry problem. And you can see right here in the stoichiometry problem we have 0.300 grams of methyl salicylate. So we have 0.300 grams of this C8H8O3. What do we do with grams right away? We're going to divide by the molar mass. They gave us the molar mass of this compound of 152.15 grams per mole, and that will convert into moles. And so we have 0.00197 moles of C8H8O3. And always put your units and what it's assigned to, and that will really help out as you go along any stoichiometry problem. Now, if you can see, they gave us a molar ratio in here. They said for every 1 mole of C8H8O3, we produce 1 mole of the salicylic acid crystals, that HC7H5O3, which means if we have 0.00197 moles of C8H8O3, that means we will produce 0.00197 moles of the HC7H5O3, and that's your little molar ratio part. That helps you go into the product there. And now we take our 0.00197 moles of the HC7H5O3, and you can see they gave us the molar mass of that compound. So times 138.12 grams per mole. I like to do this step by step. It makes it clear for AP reviewers. It makes it clear in your brain, and you can do any type of problem. We get 0.272 grams of HC7H5O3, and that is my answer. That is my product. Okay? And so that was a nice little stoichiometry problem to start off the test. Now you can see in this next problem, it says as a part of the experimental procedure to purify these crystals, the crystals are filtered, they're rinsed, and then they're dried. And they give us some properties of salicylic acid in this table. And they say the student's experimental results, it says, results in 87% yield of dry HC7H5O3. The students suggest that some of these crystals dissolved in water were dissolved in the distilled water during the rinsing step is the student's claim. And is this correct? And so it says justify the answer. And so anytime we have a justification of an answer, what we want to do when we go to, and I'm going to change this to Times New Roman, and I'm going to change this to font size 12, maybe font size 15, okay? And what we want to do is we always want to do a claim, evidence, and reason, okay? And so let's do my claim. My claim. What is my claim here? My claim is that the student's claim is something consistent with the calculated percent yield value. Okay? And so my claim is it consistent or is it not consistent? I got to determine that. Okay? Now, when we go to the evidence, let's go to some evidence here. Well, some evidence is, you can see up in my value, or up in my table, it says the solubility is 2.2 grams per liter. That is really great evidence, okay? Really great evidence. And so you can see the evidence is that the solubility of salicylic acid is 2.2 grams per liter in distilled water. That is evidence. That's the evidence that happens. But I also want to give a reason behind that evidence. I don't just want to sit there with the evidence and the claim. The reason is going to be the key step that we want to do. And so I'm saying if some moles of salicylic acid is dissolved in the distilled water during the rinsing step, then there is less moles of dry salicylic acid, and I keep spelling salicylic acid wrong, that will be measured. Therefore, the percent yield, or I'll say the theoretical yield, will be greater than the actual yield, which means I can come back here, the student's claim is consistent, and there is my claim, my evidence, and my reason. And we always want those three things anytime we justify our answer to get our full point. Okay? Let's keep going. We go to the next one. The next one says we have 0.105 grams of this, and they give us the molar mass, and they say we have 25 degrees Celsius to 159 degrees Celsius. So right away, I think we're going to do a Q equals MC change in T problem. We want the mass of the sample, which is 0.105 grams of HC7H5O3. The specific heat capacity of salicylic acid is 1.17 joules per gram degrees Celsius of HC7H5O3. And what is my change in temperature? My change in temperature is 159 degrees Celsius minus 25 degrees Celsius. And that will give me my Q, which is 16.5 joules of heat of the HC7H5O3, the salicylic acid. Okay, so that's how much heat it took to raise the temperature from 159 degrees Celsius, from 25 degrees Celsius up to 159 degrees Celsius. But that is not we still have to melt it. We still have to break the physical attractions of that salicylic acid. And take a look at this heat of fusion. This heat of fusion is 27.1 kilojoules for every 1 mole of the salicylic acid. Or you could say 27.1 kilojoules for every 1 mole. Well, how many moles do we have? We have 0.105 grams of HC7H5O3. I'm going to divide by the molar mass, 138.12 grams per mole. And that gives me my number of moles I have. That gives me 7.60 times 10 to the negative 4 moles of HC7H5O3, which means if I know the number of moles is 7.60 times 10 to the negative 4 moles of the salicylic acid, I can know the number of kilojoules of the salicylic acid by doing cross multiplying, by doing a ratio there, and I end up getting 0.0206 kilojoules of heat to melt it. That's to melt it, okay, when we're at this 159 degrees Celsius. Okay, which is, if I multiply by 1,000, 1, 2, 3, I get 20.6 joules of heat to melt. Okay, so at the end of the day, what do I have to do? I have 16.5 joules of heat to raise it from 25 to 159. I have 20.6 joules of heat to melt it when we're at 159 degrees Celsius, which means 37.1 joules of heat total. Okay, joules of heat total. And so you can see we're bringing that salicylic acid from 25 up to 159, then we are breaking the physical attractions of that salicylic acid to melt it completely. to melt it completely. Okay, you can see on to question D, they give us the structures of salicylic acid and methyl salicylate. And you can see they said the same three types of intermolecular forces. They all have London dispersion forces, dipole-dipole attractions, and hydrogen bonding. All three exist. Why is the melting point of salicylic acid so much greater than the other one? Okay, and so again, what do I always do? I am always going to do my claim, my evidence, and my reason. My claim, my evidence, and my reason. So let's go to my claim. They gave me my claim. It's okay to restate your claim. I always like to do that. The melting point of salicylic acid is higher than that of methyl salicylate. Okay, that's my claim. What is the evidence? What is the evidence of this? The evidence is that the relative amount of London dispersion forces is approximately the same for both compounds. We know that they're relatively about the same molar mass, which means they have the same relative number of electrons, which means the same number of relative London dispersion forces. It is not one of those questions where one has a greater amount of London dispersion forces, more electron clouds are polarizable. But what is the big difference? The big difference is the salicylic acid has multiple sites of hydrogen bonding attractions. Okay. On the COOH ends of the molecule. Whereas the methyl salicylate has London dispersion forces at one of those sites. There's my evidence. But I'm going to give a reason. I have to give a reason. The two areas, or the two sites, I like the word sites better, there's two sites of hydrogen bonding attractions of salicylic acid can form attractions with other salicylic acid molecules, and I'll say form stronger, and even I'm going to change it to relatively stronger attractions with other salicylic acid molecules. These greater intermolecular forces of attraction requires more energy to separate these molecules and melt them. That is a full-orbed answer. Claim, evidence, and reason. Claim, evidence, and reason for part D. Let's go to part E. Part E, you can see now we have this salicylic acid, this C7H5O3. We're titrating with a strong base, and so we have this C7H5O3 plus hydroxide. This is giving the H plus, the proton. We get water, and we get C7H5O3 minus. You can see it's a weak base. We're looking for the pKa. Remember the pKa. The pKa is halfway to the equivalence point. Is the pH is equal to the pKa. And so the equivalence point is at 10 milliliters. We're going to go to 5. 5 is about right there, which is about a pH of about 3.1. And that is good for that. Now you can see the next question says when the pH is 4. So you can see we're about 4 right here when about 9 milliliters are being added. And it says, is there a higher concentration of the weak acid or the conjugate base? Justify your answer. So remember, anytime we justify our answer, what do we need? We need a claim. Okay? We need a claim. And that claim, you can see, is there is a higher concentration of, and I'm going to fill in this, okay, in the flask at a pH of 4.00. Okay, let's go to the evidence. Let's go to the evidence here. Okay, when the titration is halfway to the equivalence point, which is 5 milliliters of the 0.0200 molar NaOH, the pH is equal to the pKa. Since there is an equal concentration of weak acid and its conjugate base. Okay? But what's the evidence is the pH is greater than the pKa. The pH is greater than the pKa because the titration is past the halfway to the equivalence point. Okay, so what is the reason? Okay, what is the reason? We need a reason. Okay, the amount of NaOH added increases as the titration proceeds and approaches the equivalence point. Okay. Therefore, the amount of conjugate base becomes greater in concentration than the weak acid for the reaction below. Okay, and you can see I'm going to write that reaction right there is my HC7H5O3 plus hydroxide gives me H2O, and my conjugate base, the C7H5O3 minus, and this has become greater, which means the concentration of C7H5O3 minus is in my claim right there. And that is going to be greater. That's a full orbed answer. That is a claim. That is evidence. That's the reason you're going to get your full points there. And that is that. Now it says, in the next question, it says calculate the pKa value. Well, what is pKa? Well, if pH equals the negative log of the H plus, then the pKa equals negative log of the Ka, which means negative log of 6.3 times 10 to the negative 5. And we get 4.20. Nice, easy question there. Let's go on to H. H says we're going to take 20 mils of 0.01 with titrating with 0.02. We're going to do the same thing with same thing that we did with salicylic acid. Okay, what did I know is the pKa is equal to 4.20. That's equal to pH at halfway to the equivalence point. Okay. They also tell me that the initial is 3.11. So you can see my initials right there. Halfway to the equivalence point, we're at 4.2, which is about right here. And you can see we're going to, because we're using the same volume, the same concentration, and we're titrating with the same thing, it's going to be the same equivalence point at 10 milliliters. And so this curve is going to be a little bit higher up here. There's our buffering region. And you can see I didn't do that great. Let me do it a little bit smoother here. And this comes up. And then you can see we have our titration curve looking like that. You can see probably the 2 points they're looking for is where you start, halfway to the equivalence point. At the equivalence point, having a pH above 7 right there. And so that is kind of what we're looking at. And that is the 2022 AP Chemistry Free Response question. Number 1, I hope that helped. Check out MrAiden.com. It's a great website. I know because I created it. Just joking. It's a great website anyway. Have a great day. Hopefully this helped.